Perfect.
Brilliant. Thank you so much, Cosimo, and everybody who organized this workshop. It's really an honor to be contributing alongside so many esteemed speakers. And we have heard very interesting ideas this morning, this afternoon, and I'm going to share some ideas as well, highlight some key points, which I think will resonate with much of what we've heard already. On the topic of model-based control of soft continuum manipulators, providing an energy-based approach. So I would like to start with a brief introduction of a rigid link modeling approach that we employ, Porter-Miltonian formulation, and a methodology called either PBC, interconnection damping assignment, passivity-based control. And then I would like to highlight some key points about how these methodologies can be applied to rigid link models, how we can deal with disturbances, what are the effects of nonlinearities, and then concluding with some results on regulation in joint space, in Cartesian space, and finally, one application. So this talk is about soft continuum manipulators, which is a subset of all soft robots. And here I intend structures that are typically serial in nature, that have some intrinsic deformability and a stiffness comparable to that of the environment. Here we see a video from early 90s in Japan. So as I think we have heard a few times already today, one of the main characteristics of soft continuum manipulators is deformability, which I think we agree can be associated with the high number of degrees of freedom. And typically we end up having more degrees of freedom than we have sensors and actuators. And on top of that, of course, we have nonlinearities. Let's see if I can get a pointer here. Yes. So these figures basically are just to show that the difference between the planar rigid robots, where we have actuation and sensing concentrated in specific points, and planar, in this case planar, but in general soft manipulators, where deformation occurs in a continuous fashion along the axis. This figure is one of our prototypes, which are made of silicon, and this is what I'm going to talk about in the specific. They have internal chambers, which we can inflate and to achieve bending on any plane. And our manipulators, they are by construction inextensible. So there are many ways to model these type of systems, and actually we've seen a few today. What we use is a fairly simplistic approach, which relies on the idea of rigid link models with virtual elastic joints. This concept stems from the idea, well, the work on pseudo rigid body models, which appeared in early 2000. And it's a way to describe the relationship between stress and strain in compliant mechanisms. And a similar sort of approach has been employed for soft continuum manipulator by different groups, including Clemson and Vanderbilt, and here I'm citing one reference. So it is important to keep in mind that this is an approximation, however, it does capture some important features of soft continuum manipulators. In my opinion, the most important of which is this arbitrary high number of degrees of freedom, depending on how accurate we want to be. This as shown in this simple schematic. So as we said in our prototypes, typically we can achieve bending by inflating the internal chambers. And so on a plane, we would have one actuator, let's say, and in this case, an arbitrary number of virtual elastic joints. The main parameter here, apart from the number of joints, is also their stiffness, which is basically defined so that to match the mechanical characteristic of the prototype. So there are many ways, again, to express or describe the kinematics of such systems. We use a Porter-Miltonian formulation. And the reason here is very much along the line of what Stefano said this morning, is because it's energy-based, so it hinges on this definition of Hamiltonian, in this case, as total mechanical energy. And this makes it, at least in principle, very general. So it can be applied to different domains. So here we see in this equation, we have our states, position, and momenta, so product of velocity and inertia. We have the control input, which acts on the state through this input matrix G, which in case of underactuation is rank deficient, so it's not invertible. So taking advantage of this formulation, we use one methodology, which is the interconnection and damping assignment, passivity-based control. This was introduced, to my knowledge, by Romeo Ortega. The main idea of this approach is to design the control action such that the closed loop dynamics is also Hamiltonian. So we see that this matrix here is Q-symmetric, and it is associated to a different total energy, or Hamiltonian HD, where the inertia matrix MD and the potential energy are design parameters. Why did we choose this approach? Well, because it lends itself very well to low gain, let's say, controller designs. And there are now a number of, I think there are a number of results, and there is general agreement that using high gains for soft continuum manipulators, it can be, can lead to problems. Low gains, on the other side, help us to preserve the stiffness in the closed loop. So how do we go about to apply such a methodology? Well, we said typically we deal with systems that have less actuators than degrees of freedom, so G is not invertible. And this means, in an analytical sense, that we have additional constraints on our parameters, our inertia matrix and potential energy. We can define these constraints typically as partial differential equations. So to do that, we define this operator, G orthogonal, which is the null space of G, and then we proceed to matching the open loop dynamics with the closed loop desired dynamics on the unactuated states, basically. This gives us analytical conditions in the forms of PD on the inertia matrix, on the potential energy. And on top of that, we also need to ensure that the closed loop Hamiltonian and potential energy in this case have some desirable properties that relate to our control goal. For instance, regulation, which is the typical goal for this approach, can be enforced by making sure that the potential energy has a strict minimizer at the prescribed equilibrium. So provided that these PDEs are solvable analytically, then we are in the position to compute the control law with this equation given in this at the bottom of the slide. So let's see now how we can apply these methodologies to rigid link models. And here, my aim is to highlight some key points, which some of which I think have already been discussed through the day. So the first is related to the internal dynamics. So if we think of typical classical examples of underactuated mechanisms, such as inverted pendulum, typically we have an unstable internal dynamics with isolated equilibrium points, either the upright position or the bottom position. In this case, the situation is quite different. So if we look at our rigid link system with virtual elastic joints, we don't have isolated equilibrium points for the internal dynamics, but we have a continuum, so basically a set of equilibria. And we could compute that analytically with this equation. So G orthogonal multiply the gradient of the potential energy. This in the absence of disturbances. So this allows us to move from regulation, which is the classical goal for AWPBC, to potentially path following. Another aspect is related to output feedback. So as we heard this morning, we typically have more degrees of freedom that we have sensors. So ultimately, this means that we are typically not able to provide full state feedback, which is which is a further obstacle, let's say, on our track. And this basically results in further constraints on the PDEs because we want to choose a solution such that the resulting control input is implementable. It only depends on those combination of states. We can call them output. I prefer not to do so, such that it is implementable. The other element is related to damping. So in physical systems, in mechanical systems, typically we have damping which is not negligible. So we need to account for that. And if damping is often is the case, affects all states, then we are not able to cancel it on the unactuated coordinates, let's say. So what is important is that we are aware of that and we make sure that the damping in closed loop, so this matrix D, is positive definite. This is important for stability reason, as we will see in a few slides in more detail. So what's the result of all this convoluted process? Well, let's see a simple example with n equal 3 virtual elastic joints with the constant uniform stiffness. If we go through all the steps, we end up with a fairly simple control law, which has a feed-forward term depending on stiffness, a feedback term depending on the output error, and a derivative term. So this does not take into account external forces or disturbances. However, we need to do that because they are present in engineering practice. So to account for disturbances, first of all, we need to, let's say, do so in the open loop. And we can do that by introducing this term delta. And we also need to account for their effect in the closed loop. And here, of course, there are many ways. The main idea of this approach is to introduce this vector of closed loop non-conservative forces and then proceed to matching the effect of the disturbances on the unactuated states between open loop and closed loop. The benefit of this is that it preserves all the work we have done so far on the PDEs for the disturbance-free case. We also need to make sure that the prescribed equilibrium remains a minimizer for the closed loop potential energy. So this is a fairly general approach. It applies to underactuated systems, and the result is an additional term in the control law, which depends on our projections of disturbance and in the open loop and closed loop on the matrix G. So what is interesting also in my opinion is that the presence of disturbances or external forces, whatever you want to call them, as a repercussion on the assignable equilibria. So the set of equilibria that are actually achievable. And we can do that, we can see that in this equation where we account for the disturbance alongside the gradient of the potential energy. So as we will see, depending on the type of disturbance or external force, this means that some configurations, such as the constant curvature, are not assignable in some cases. So for this slide, we assume for simplicity that the external forces are measurable. This can be true if we have force sensors. More often than not, that is not the case. So the need arises to estimate these disturbances in one way or another. One way to do that is to introduce an observer which estimates the disturbance or the unknowns adaptively. For example, from the open loop, and this is indicated here in a general way with this observer state delta hat. We can design, of course, the observer using different techniques, and I'm not going to go in particular detail, but the aim of our design would be in general to ensure that the estimation error, Z, so disturbance estimate minus the actual value, converges to zero, ideally exponentially or asymptotically, or at least it is ultimately bounded, depending on the method you apply. Regardless of what we choose, we would then be able to replace our unknowns in the control input with our observer state. Here, the key points I wanted to highlight are the following. So the first of all is again related to output feedback. Our choice of this observer design is still constrained by our ability to only measure some combination of states. So this is to ensure that our control input, our control law is actually implementable. The other aspect is related to stability, and it is basically linked to the type of observer design we choose. So regardless, so we actually know, depending on whether we achieve a specific dynamics of the error, this would have repercussion on the closed loop dynamics, because that is in a way coupled with the aerodynamics itself. What it means for us is that the stability conditions would change, and the tuning guidelines, which we can extract from the stability conditions for our controller parameters, would also be affected. We will see in more detail what this means in a few slides. So another approach that we can use to deal with unknowns, disturbances, model uncertainties, or external forces is a more sophisticated version of EDA-PBC, which is called integral EDA-PBC. And here the expert is really my co-author, Alejandro, in Australia. The idea of this approach is to include a further control action, V, such that the closed loop dynamic corresponds to an extended dynamics, where we have an extended state, this zeta, and a number of parameters, these terms S, which we design by matching the closed loop dynamics with the extended dynamics at each level, so basically at each row. And defining a new storage function, this W prime, which includes the Hamiltonian, the effect of the external forces, and our extended state. So again, we come face to face with the same limitations we had before, so output feedback. However, if we are able to solve this matching, then we end up with a control law that includes an additional term, which is an integral action. Here we see that the integral action includes the effect of damping. So linking back to what I mentioned before in previous slides, damping is something that we have to account for, and actually has repercussions at several levels, both in the control law and also in the stability conditions. So let's move on to see what the effects of nonlinearities are on our controller design. So the main idea here that I want to share with you is related, in my opinion, to the concept of design of control. And here I mean how design and control actually interact together and kind of can help each other in a way to achieve a given goal. To explain better what I mean, I'll give two examples. The first is the example of nonlinear stiffness. Here we consider a polynomial description of the stiffness, where Kj are constant parameters. If we try and solve our PDEs, we see that actually they are solvable for any value of the position of our virtual joints, if and only if K0, so the constant part of the stiffness, is not zero. So this means that we can indeed construct a control law, and that this control law is valid for any configuration of the joint position. If, however, K0 happens to be zero, we can still solve the PDE, but only for the case Qi equal Qj for any I and j, which is the constant curvature configuration. So what this means, in my opinion, is that the structural stiffness, or in general the key design parameters of our system, and also the way we model them, have a direct implication on our ability to construct a control law, and also on the validity of this control law among the range of operating conditions. The other example is related to nonlinear damping, and now this affects stability. So here, perhaps a few words to say that damping was originally neglected when the PVC was formulated, and has since been seen as an obstacle in general for underactuated systems, and rightly so. However, we will see that this is not necessarily the case all the time. So if we consider pneumatic system, the literature tells us that we typically have nonlinear damping that we can express as a polynomial. Without going through all the derivations, basically what I can anticipate is that if we study the stability of our closed loop equilibrium with our proposed control law, we come up with an expression which is negative semi-definite only if and only if these coefficients defined in the damping are positive. So what I wanted to highlight here is, on the one hand, that the tuning guidelines which we can extract from the stability condition are directly related to the damping terms. On the other end, we can look at the problem from a different side and see actually we can perhaps act on the physical prototype, modify the damping. We can do that in pneumatics, but by introducing flow restrictors. And in that way, we can, let's say, expand or let's say expand the range of tuning parameters that we can apply to ensure that our closed loop equilibrium is remaining stable. So another aspect very quickly is related to the regulation in Cartesian space. I thought to present this as an example of a higher level of complexity. So far we talked about regulation in joint space. And what happens if we want to regulate in Cartesian space? The good news is that we can we don't have to throw away everything we've done so far. We can build on top of it in a modular fashion. So in the presence of external forces, we typically have an uncertain mapping between joint space and Cartesian space. There are many ways to deal with that. And this is just to illustrate that we can estimate this uncertain mapping with an integral action. And we can actually then combine this integral action with our control law. And here the two key points I wanted to highlight are that this operation is possible, but we need to also introduce additional terms in the control law to make sure that the stability properties that we achieved in the first place are preserved to an extent. However, regardless of that, we need to also, let's say, see investigate to analyze the effects of what the additional tuning parameters that we introduce are on the remainder. So basically, perhaps in better words, dealing with a more complex system is possible in a modular fashion. However, both the controller, the structure of the controller, and the interaction between the different tuning parameters need to be taken into account. Another thought, which is I think more obvious, is that when we deal with systems that combine different actuators connected in series, we find that, well, in this case, due to the inextensible nature of our prototypes, that we have coupling between the mapping between joint space and Cartesian space, for example, on a bending plane. This coupling is reflected in our integral action, and ultimately is also reflected in our control law. So it perhaps relates to what we've seen in previous presentations, and the bottom line is that if we can take into account this coupling, we end up with better performance. So now very quickly over a set of results, and here again the idea is to highlight some key points. First of all, the effect of external forces. Here we consider a tip force on our rigid link model. We see that if the tip force is non-zero, the positions Q1 to Q3 stabilize at different values. So we don't have a constant curvature configuration. What is interesting is that even if F0 is 0, and if we zoom in at the first instance at the transient, strictly speaking, we also don't have a constant curvature. So in a way, this approach allows us to see this phenomenon, which perhaps would not be noticeable if we were to apply a different controller design, just looking at the output, let's say. The other point is, how does this energy shaping approach compare to other controllers? In this case, the PID, but we have repeated this for other benchmarks as well. So it is certainly possible to achieve the regulation goal for our tip orientation in this case with different controllers. And it is certainly possible to tune the parameters to even, let's say, match the transient's response. What we've seen, however, is that once we fix the tuning parameters and we change the magnitude of the tip force, in this case by a factor of 20, the energy shaping approach is much better able to preserve the performance compared to, for example, a PID in this case. Another set of results, basically they...
Enrico,
yep.
sorry. So we are already beyond the time limit, so maybe you want to...
Oh yeah, I can conclude. Apologies.
Okay,
yeah, so basically very quickly, here we have basically showing how the experiments and the simulation are very are similar, at least visually, because we've used the same parameters in both cases. And the point is to show that our modeling approach, even though is approximate, is actually representative, at least for this time scale. And the tuning guidelines, which we used for our simulations, are in fact realistic. We can use those to choose the parameters that will work in the real life. Final consideration is about comparing different observers. Here we see that we can achieve regulation in Cartesian space, employing very different observers, one with very strong convergent properties, one which is much weaker. In both cases, we can achieve the regulation goal in a similar way. So this, in a way, gives confidence that this consistency or in the face of external forces is not down to the observer itself, but to the energy shaping approach in general. So a final slide, just to show one of our applications. This is our work, which is mostly related to surgery. We see one of our prototypes operating inside a cardiovascular phantom. And here we're using a joystick to set the prescribed value of the orientation, and then the controller basically achieves the regulation goal. We're also able to estimate the external forces adaptively with an observer and feed them back to the operator in the form of vibration. Finally, I'll skip this. Just a quick thank to everybody in our group who's working on different aspects of control, design, and modeling of soft robots, and to our collaborators in different countries. Thanks again for the time, and sorry for overrunning. I'll stop sharing my screen now.
Thanks. Thanks, Enrico. Thank you very much. Very cool talk. And Stefano is already raising his hand.
Thank you very much, Enrico, for the very nice talk. I have a question. You use the IDA PBC, which is very nice, but one of the problem with IDA PBC is that it results in state feedback when you solve the PDE,
yep.
Right? And you know, state feedback can be problematic because it's not very robust for model uncertainty, for example. Mm-hmm. And it has also, IDA PBC has this problem of, dissipation obstacle, but I don't think that's the problem in your case very much, but the first one may be. Could you comment on that? And have you looked at also methods-based, energy-based, like, for example, control by interconnection, which would not have this robustness problem?
So I haven't implemented control by interconnection for this type of systems. The robustness problem is the way we approach it is basically with lumping all the unknowns, all the uncertainties within a disturbance term, and then either compensating that with the adaptive observer or with the integral action, so as a further layer of complexity around the PBC. But it's certainly worth looking at control by interconnection. Dissipation, it can be an obstacle. In this case, it depends on how we solve the kinetic energy PD. If we solve the kinetic energy PD in a certain way, then we can ensure that the closed loop damping is positive definite. So actually, we do not have, let's say, degraded performance from that side.
Okay, thank you very much, Enrico. Nice talk.
Thank you.